So we've talked about light as having characteristics of a ray when we did geometric optics, and now we'll look at light in a different way, thinking of it as being a wave. And so we have to go back and remember some stuff about waves.
And then we'll get into more complex stuff in the next couple of lectures. But just to review a little bit from 151, a wave, as you know, is a disturbance that moves over distance. Okay, so when a rock falls into a pond, it sends waves out into the rest of the pond, in this case in a circle. This disturbance often repeats itself, as when you're playing a trumpet or a speaker cone or all sorts of different waves, and we call that repetition an oscillation. So the wave moves up and down in a repeated pattern. We can talk about the frequency and the time period. So the time period is how long one oscillation lasts, and that's capital T. The frequency is in units of 1/seconds or hertz. So if something is 60 hertz, it happens 60 times a second. The speed of propagation, that is the speed that the wave is moving through space, is related to wavelength and frequency, right? So wavelength is this distance between the peaks of our wave. And if we multiply our frequency times our wavelength, we'll get the velocity over the wave, the speed of propagation of the wave. The amplitude is the height of the wave, or really half of the height of the wave, because it measures from the average middle point to the peaks, both up and down. And that's a sort of general, we can say all that stuff about any wave. Electromagnetic waves in particular are still a disturbance, and the disturbance in particular is the oscillation of an electric and magnetic field. So we can think about the way here that an AC wire creates a magnetic wave. So at time zero, let's say we have a wire here. We create an electric field in that wire, right? And that drives our positive charges up or our negative charges down. Okay. At T/4, the voltage has returned back to zero. So initially it shot up, but then it starts alternating. This is the alternating current symbol. And this disturbance in the field is communicated in an EM wave that moves away from the wire. Okay, so you have this current that's moving back and forth here, and that changing current creates magnetic and electrical fields. This is the wave moving away. So this is the field that was created at time equals 0, right? Is now moving away. At time over 2, here's the field that was created at time over 4. That's now moved to here. And our time equals 0 part of the wave has moved to here. And then we continue to move. So at time equals capital T, that is one period. We're back where we started originally with a voltage that's high in this direction. Our T equals 0, the point that was propagated at T equals 0, is now one wavelength away from the wire. And then here was the point that was propagated at T/4 and T/2 and 3T/4 and so forth. And so this creates a disturbance that is carried through the distance as a changing electric and magnetic field. Okay, there are a couple of differences between EM waves and other waves. One is that an EM wave has two components. We've talked about electrical and magnetic waves and the connection between them. If you think about a wire here, and let's say we have a current running through there, our magnetic field is around the wire. And so at any given point around the wire, the magnetic field might be in this direction. Well, the electrical field is up and down. right? Because it's in the direction of the wire itself. And so these two fields are perpendicular to each other. And so as that current alternates in the way that we talked about on the previous slide, the wave propagates away from the wire in two different directions. You have a magnetic field that disturbance is propagated as a wave, and then you have an electrical field disturbance that is propagated as a wave. These two are perpendicular to each other, and so they're oftentimes pictured in this way here. The second way that they're different from most other waves is that most waves, we talk about a medium, right? If we have a lake, the medium is the water. If we have a sound wave, the medium can be the air. If we have a wave that's going through a slinky, then the medium is that string or that, steel wire. EM waves can travel with no medium, and that makes them unique. Just as, light travels through space. So the EM waves that are the visible light coming from the sun travel through a vacuum to get here. If they didn't, we'd be in real trouble. Dead. Actually, we'd just not exist, I think.